All right, welcome to what would have been lecture 22 on April 9th, 2020. Let's get to it. So today's goals, we're going to talk about solutions a lot. So we're first going to talk about the solution process, and you want to get to know the basics of that. We're going to introduce strong and weak electrolytes, talk about how to figure out exactly what species are present in a solution. We're going to predict solubility or relative solubility based on molecular structures and intermolecular forces. We're going to predict the effective temperature and pressure on solubility. All right, most of what we know about the nature of the solvation process and what's actually floating around in solution comes from our study of electricity and how they go through water or how they go through solutions. So it turns out, you might not know this, but pure water is actually a fairly poor conductor of electricity. In fact, so the device that we use in the back of the lab to purify our water, the way that it actually checks that it's doing its job is to see that the water is not conductive. If it gets too conductive, an alarm goes off and we have to change the filter, get it fixed, or whatever. Now, it turns out that if you put certain compounds, namely covalent compounds, many of them anyway, that like sucrose, for example, doesn't conduct electricity either. Now, one thing that this graphic doesn't show you is, moving on to sodium chloride here, is that solid sodium chloride, so pure water doesn't conduct electricity. Pure solid sodium chloride doesn't conduct electricity either. So you could fill a beaker in with solid sodium chloride, and the circuit here, the way that it works, let me get that pointer here for you. You've got these electrodes that are in the solution. And if the solution is not conductive, you've got an open circuit, the light bulb doesn't turn on. Pour in the sucrose, still an open circuit, no light bulb. If you were to fill this beaker with pure solid sodium chloride, it also would not conduct electricity. Light bulb doesn't go on. But if you would put just a pinch, you don't have to pour it in from the container here, but literally just a pinch of salt in the water, all of a sudden that solution becomes very conductive. And it doesn't take much. So, public service announcement, tap water has more than enough stuff dissolved in it to be conductive. So tap water is conductive, so don't run a light bulb wire through your bathtub. All right, and the other thing to note is that if you were to take pure sodium chloride and melt it, that resulting liquid also conducts electricity. Now, we talked about this in when we talked about just describing various types of solids, that what's necessary for electrical conductivity is a mobile charge carrier. So sodium chloride is chock full of charge carriers. Pure solid, they aren't mobile. Pure liquid, they are mobile. And apparently, when you dissolve it in water, you get mobile charge carriers too. Now this becomes a conductive solution. We have a name for that, and that is electrolytes. So this word right here. So what's actually going on here? Well, here's a cartoon of the dissolution process, which we actually call dissociation. So that's one of the words for today. Now, for this, two things have to happen. I'm going to describe them sequentially, but they sort of happen simultaneously. First thing is that you have to break the ion-ion interactions in the sodium chloride, as shown here with this nice, very ordered array. Now this is an ionic solid. These are very strong ion-ion interactions. What people also don't think about is that you also have to break the hydrogen bonds in water. You can't put these ions, you can't have them, you can't dissolve them in water without separating the water molecules and actually physically making space for them. So water-hydrogen bonds, we talked about that being a relatively strong intermolecular force too. So now both of these by themselves are going to cost energy. They're endothermic because you are breaking an attractive interaction and not necessarily replacing it with anything else. But in the end, something does happen. Once you break apart the water molecules and break apart the sodium chloride crystals, you now have the opportunity for very strong interactions that we now are calling ion dipole interactions. So water is very, very polar. The negative end, that would be, the oxygen atom, is going to be very strongly attracted to the positive ions, the sodium ions in this example. And for the chloride ions, it's the other way around. They have a negative charge, so they're going to be quite strongly attracted to the positive end of the water molecule, the hydrogen atoms. And what's important to note is that at this point, there's hardly any interactions or no interactions at all between the sodium ions and the chloride ions. They're far enough away from each other now and are quite happy to interact with the water molecules that they don't interact with each other anymore. And that's why you don't see the crystalline solid anymore. Now these ion dipole interactions are quite strong, and here you are making an attractive interaction. So that process releases energy. It's exothermic. Now the question is does this release more energy than the breakup of the salt crystal and the hydrogen bonds in a water molecule require? And in that case, the overall process will be exothermic, and if it's not, it'll be endothermic. More pictures coming. So whether or not the overall process gives off heat or requires heat